right, welcome back to operating systems in this boiling room. Why is it like this in October? I have no idea. So, everyone's favorite topic is about to come up, virtual memory. So, before we start that, let's ask a question. How should we implement it? So, all we have to do for virtual memory is find out a way to map virtual addresses, which should be independent per process, to a physical address, actually residing in memory. So I will take a little detour just in case you've Discord open. If not, we can discuss it. And that question is simple. What are your ideas for how to map this? So I will paste that. So any bright ideas for how to map, actually physically implement the mapping from virtual address to a physical address? So, yeah.
Let's say if I basically at least find chunks of unused memory that you can put aside for processes, and then give that chunk of memory and assign it new values for the process, and then value that process memory.
Yeah, so find some chunks of memory, give it. So yeah, that could work for actually finding physical memory, but what about actually doing the translation from virtual to physical? Like, how would you implement that? Yeah.
It's offset with some sort of chunk size based on the
So if it requested a big chunk size, just kind of calculate it, figure out its offset, and just like map it one-to-one somehow?
Yeah, so if you wanted to get the location 1 for the PIA intent, you would have a take 1 gig of that process, or your chunk size is 128, multiply by the process that you
So you could give each process just a chunk, like a fixed size chunk, and that's it? Could do that. Any other ideas? So what about, I don't know, crazy. We want to look up something. What about a hash map or something like that? Does that sound sane at all?
Well, how is
Yeah.
it better than just using a preset and place a chunk and everywhere, like just indicating the preset?
Yeah, how's a hash map different than a chunk and what?
Yeah, I mean, how is it better? I mean, you need to search the hash map and
Oh, how is it better?
yes, how is that?
So it's a bit more flexible, right? We could just map it to any arbitrary. We don't need everything all in a row. That could be one. Yeah.
But then it's also not, it's not super conforming. You have to access memory all over the place.
Yeah, you might have to access memory all over the place. And remember, memory is byte addressable, right? So every address represents a byte. So if it was a hash map or something like that, addresses are like 64 bits or 8 bytes. So my hash map would need to be keyed by a virtual address. So that's 8 bytes, and its value would be like a physical address. That's 8 bytes. So that's probably a bad idea, because for every byte, I need 16 bytes to keep track of the mapping, even if the rest of it was free, which is not. Probably not a good idea. Got another one. Divide up memory into small chunks and work it with our hash map. So hash maps, you should have implemented one. Hash maps are basically just fancy arrays that just do the indexing for you. So it essentially just fakes a large index, makes it into a smaller one, but hash maps are essentially arrays. So if you can just get away with arrays, that's also probably faster. So let's go with the first idea. I like the first idea of having just blocks that represent stuff, and then you could just calculate it, right? So in fact, you have described, you've described a technique we'll use, but first we'll keep this checklist in mind. So remember, with virtual memory, needs to be independent for each process. So multiple processes have to be able to exist at the same time. They shouldn't be aware that they are actually physically sharing memory. They shouldn't be able to access each other's data unless they're explicitly allowed, which we'll see how to do that later. It's a type of type of way to communicate between processes, but by default, everything should be independent for each process because you wouldn't want another process to read your passwords or your private key or whatever. We also want good performance, so close to using physical memory, and to limit the amount of fragmentation, which is just a fancy word for wasted memory. So my hash table idea would obviously fail at the last point, and it would performance would probably also be fairly terrible. So here's just so we remember, memory byte addressable. So the smallest unit, every address represents a single byte. You can read or write 1 byte at a time minimum. You can't just access individual bits. You just get 1 byte at a time. So you can think of like an address as just an index into a byte array. So each address uniquely identifies a single byte. Memory is basically just one big array of bytes if you want to think it that way, with the address being the index. So your idea was essentially segmentation, and they're fairly coarse-grained. So you could have a virtual address space for like code, data, stack, and heap, and it kind of corresponds to an ELF file or what your executable file looks like. So it's large sections of memory with different purposes and different permissions. So like your code, that's something you would execute and read, probably not write. Data, you might just only read it. Your stack, you would read and write. Same with your heap. So each segment can be a variable size, dynamically resized, and this is a good idea, and it was used back in the day in the 70s, but it's no longer used. Primary reason for that is those segments are really costly to reallocate because they have to correspond with a big block of contiguous memory. So if you want something to grow and it can't quite fit, well, you might have to move all of that memory somewhere else, copy it to make sure it is in one straight contiguous line. And another thing is it might lead to a bunch of fragmentation because we have variable size things. Some allocations just might not fit. We might actually waste a bunch of memory. And this was used in the 70s and not used in modern operating systems. So how it worked, oh, sorry, was there a question?
I was just gonna ask, like, coarse grain in this case being like kind of like super simple and not very fine.
Yeah, coarse-grained is like, I can't really share anything that's not part of a segment. So like I can't, if I wanted to share code between two processes and like fake a mapping or something like that, I couldn't do it in this case because I can only map one big block at a time, right? So I might be able to do it with like two processes, but past that I can't do anything. And I just have a segment for each individual thing. So it like kind of works, but we'll see. As we go on and understand what actually happens, we'll see some more disadvantages to it. But it works. It will get a bit messy once you add features on top of it. But at its core, each segment, it's a pretty good first estimation of it. So each segment would contain a base physical address. So where that segment actually starts in physical memory, a limit, basically the size of the segment, and then permissions, read, write, execute, something like that. And then you get a physical address by using this as your virtual address. So it splits it up into two parts. You first ask for a segment, which is called a segment selector. Basically just a number that says what the segment should be, and then an offset. So how many bytes from the beginning of that segment is the information I actually want. So offset will always just be the number of bytes from the beginning. So the MMU, or the memory management unit, which we'll get into later, whatever it checks if the translation is valid, it's going to check if the offset is within the limit of the segment you're currently in, and then if it's within the limit, it'll check permissions. Then after that, to do the actual translation to get the physical address, it's just a simple addition. It's just the base address plus the offset. That gives you the physical address. Otherwise, if it is out of bounds or the permissions don't check, you get a segmentation fault, which you have all heard before. So whenever you try and dereference the null pointer or whatever, it's called a segmentation fault. For fun fact, your computers don't use segments anymore, but it's still called a segmentation fault because if it's any term that you see, well, guess what? We went through that whole library thing where you're never allowed to change anything. So that's why it's called a segmentation fault. even though once we go through this, we'll figure out that, hey, they don't use segments anymore. So if they did use segments, your virtual address would look like this. So this means select segment 1, and I want to do offset FF, which is like 255 bytes into it. And then as part of your description of the segment, which your kernel would manage, it would say, hey, segment 1 starts at physical address 2000 in hex. Its limit is 1FF or size. And then when it did this translation, it would see that, oh, FF is less than 1FF, so this is within bounds. Assume that it has the correct permissions. So to calculate the physical address, it would just do 2000 in hex plus FF to give you 20FF. That's your physical address. So what Linux does to get around it, because your like old x86 hardware still has support for this because they cannot take it out, they set the base to every segment to 0 and then the limit to the maximum amount of memory you have on your machine. So essentially it turns segmentation into a no-op where it just doesn't translate anything. So the address is just the offset. So we also like the other idea, so we're kind of on the right track of dividing memory into chunks. So the easiest thing to do in terms of allocating things is to divide memory into fixed size chunks. So everything is the exact same size, and it makes allocation a lot easier. So that way, we just pick a virtual block with whatever size it is. So these numbers represent offset. So like 0 bytes into the page, 1 byte into the page, 2 bytes into the block, 3 bytes into the block. And then if we need to translate, we just translate the blocks. So you wouldn't need to translate where you are within a block. You just need to do the translation for a block. So our only question now is like, how big should this block be? So that will be an engineering trade-off, and someone found a good trade-off in like the 80s. So the MMU, or the memory management unit, that is the actual hardware on your CPU that is doing the translation of a virtual address to a physical address, and also does all those permission checks I was talking about. So this dividing up memory into fixed size blocks, well, we call them something special in operating systems. We call them pages. So a page is just a fixed size block. Pages are typically 4096 bytes, which is that magic number I was using in some of my code examples. So the reason I was using that number is because that is how the operating system deals with memory. It deals with it in those fixed size blocks, and they are of 4096 bytes. So there's going to be some terms as we go through this. So a page in virtual memory, generally you just refer to that as a page or virtual page. And then if you have a page in physical memory, sometimes people call that a frame. Sometimes they'll call that a physical page. Sometimes they will just call that a page if it's obvious that you mean physical memory. So another thing we all have CPUs that have 64-bit addresses. Typically, you don't have that much RAM on your machine, and you wouldn't need to use all 64 bits. So CPUs, as we will figure out, have different number of different sizes of virtual address spaces that they support, but the implementation details are the same. It's just a trade-off with some of the data structures and how slow some things are, which we will see. So in general, right now, to this day, if you have a 64-bit machine, you have a 39-bit virtual address space. So that means within a process, you can only use, at most, assuming the kernel doesn't do anything, limited by hardware, you can address at most 39 bits of memory. So that means you could address up to 2 to the 39 bytes of memory, which would be 512 gigabytes of memory. So that is the maximum amount of memory your process can actually use. The machine could actually support more memory. So this is something called SV39 in RISC-V. Every system will call it something different. And how it's implemented is there is a page table, and it is basically a giant array. So the page table will be indexed by the virtual page number, and all the entries in that page table are essentially going to be physical page numbers. So we just do a quick lookup in a table and then substitute the virtual page number for the physical page number, keep the offset the same, and now we have a virtual or a physical address. So in a diagram, this is what it looks like. So our virtual address, if it is 39 bits, well, then our offset, or where we are within a page, depends on how big our page is. So if we have a page size of 4096 bytes, well, we need 12 bits to be able to address every single byte within a page. So why is it 12 bits? Anyone want to tell me why it's 12 bits? Yeah. So the offset is like which byte in the page you are. Yeah. Yeah, so to the 12 is that page size. So this page size of 4096, why is it so hot in here? I wish the AC was not broken. So if we want to address any single byte within a page, we have to be able to address 4096 bytes. So we would need 12 bits to do that, because 2 to the power of 12 is 4096. So that's where that comes from in our offset. So the size of the offset is determined by the size of the page. So if we have a 39-bit virtual address, and we know 12 bits have to be used for saying what byte are we accessing within a page, that means we would have 27 bits left over, because 39 minus 12 is 27. So that 27 bits would be used for our virtual page number, which is basically just an index into this page table. So this page table would need 2 to the 26 entries, because we need to look up a maximum of 2 to the 26 virtual page numbers, which would be the indexes. And then this page table essentially would just be a giant array of physical page numbers. So if we were to translate a virtual address, we would get the index from these 27 bits, use it as an index into this page table, which has the physical page number, and then we would just substitute that in for our physical address, and that would be our physical address. We keep the offset the same where you are within a page, because it's going to be the same. We want to make this as fast as possible, so they would all be aligned. So there's also a nice reason why this is 12 bits, because typically we write numbers in hex. So can anyone tell me how many bits a single hex digit can represent? 4, right? So the nice thing about this number is, well, if each hex digit is 4 bits and an offset is 12 bits, how many hex digits would represent an offset? 3, right? So 12 divided by 4, 3. So 3 hex digits represent an offset. I don't have to translate them. Makes it really, really fast. I don't have to do any math. So the entries in that page table, like I said, the most important thing is this physical page number, which in this case is 64 bits, but this is the entire, what the page table entry looks like in its entirety. So because it doesn't have to translate the offset, the important part for translation is this physical page number. So some of the other information in this is used for permissions for the entry. So the most important ones for us is this valid bit. So if it's 1, it means the page table entry is valid and I can use it for translation. The other ones that are important for this course are, is this memory readable? And then, is this memory writable? That's it for this course. There's other ones you could imagine which would be useful. Is this memory executable? The user just means, should this only be valid in user mode? Global means, is this mapping the same for every single process? Then there's like access bits, and then dirty, which get your mind out of the gutter. That just means that there was a write to the page and it's been modified. It doesn't mean what you probably think it means. Then there's like 2 bits that are reserved for supervisor use or the kernel use, which you will find useful when you do this yourself in Lab 3. And then they reserve some 10 bits just for future use. They could extend the physical page number if they really wanted to, but for now, that's like, they have 56 bits for physical addresses, so that's enough for this foreseeable future. But if they wanted to, they could expand it if they wanted to. So, the kernel is what keeps track of all the page tables, and if we have a simplified version of our page table where we'll just list like the virtual page number, which is the index, and then which physical page number that maps to, this would mean that virtual page number 0 maps to physical page number 1, virtual page number 1 maps to physical page number 4, so on and so forth. So, if we have to do the translations where on the left is a virtual address and we want to find the physical address, well, to do that translation, first you find the offset. The offset is 3 hex characters. So we take AB0 and just write them for the physical address. We don't have to translate them. So the last 3 hex digits are going to be the same. So they would be the same in the physical and the virtual address. So that means if it is not the part of the offset, it means that this is the virtual page number. So all you have to do is look up virtual page number 0 in this table, figure out that it corresponds to physical page number 1, and then you just do the substitution. So our physical address would be 1AB0. Not too bad, eh? Same thing for this address. So you don't have to translate the last 3 hex digits, so it's FA0. Same thing in the physical address, and then to translate this virtual page number, it is virtual page number 1. We'd look it up in the table, get physical page 4, just substitute it, and this would be our physical address for FA0. Yep. Sorry? Yeah, so all your processes, they only use virtual addresses. So every address you see is a virtual address. You will only ever see physical addresses if you are the kernel. And most kernels actually use virtual memory as well. Yeah.
Does that mean like an operating system is basically has to be written for a certain memory?
Sorry?
Like an OS has to be written for a certain MMU.
Yeah, so the MMU is like the actual hardware that does the translation, and the kernel manages all the page tables that the MMU uses. So like the kernel would be responsible for these tables, and then the MMU would be the hardware that uses the page tables to do this for you. So it automatically does all these using the page tables.
But if the MMU changed, you still use the same operating system.
So the MMU is like the physical hardware. So if the MMU would just, so this would be part of the definition of the MMU. It would define a page table entry and how you're supposed to use them. So yeah, you would just have to follow whatever that CPU says. So it would have to be formatted exactly like this. Then we have one. The page table entry translates the virtual to physical, but how come in the PT example it doesn't have a virtual page number? So the virtual page number is essentially just an index into this page table. So it doesn't exist in the page table entry. It is how you find a page table entry. So this virtual page number is an index. I use it to get the index into my page table. It gives me the page table entry, and the important part of the page table entry is this physical page number, which is why we did these translations. So any questions about these translations? The last one makes sense. All right. So if there's any questions about those translations, ask now because it's. So remember how processes started off okay and then got real weird real fast? This will get weird fast. All right. Same page. We're all good? All right. Then let's try a question to see if we remember this. So I can describe any system and you should be able to figure out how to do some translation. So in this system, let's assume I have an 8-bit virtual address and a 10-bit physical address, and then each page is 64 bytes. So we have to essentially do what we did before, except the numbers are a bit weird now. So you will probably get asked questions like, hey, how many virtual pages are there? How many physical pages are there? How many entries would there have to be in this page table? And then given a page table, actually do the translation. So I will give you a second or a minute to think about this, and then we'll go through it. So think about how you would get each of these answers and what this system would look like. All right. Do you have any ideas how to start yet? Yeah.
Well, each page is 64 bytes. I would have to assume that offset would be 6 bits.
Right.
2 to 6 is 64. So that'd be 6 of the 8 virtual address bits that would be the offset.
Yeah. All right. Everyone agree with that? Everyone heard that? So first part of this is given the page size influences how many offset bits I need to say where in the page am I. So if I have a 64-byte page and memory is byte addressable, that means I need to be able to access up to 64 different locations within the page. So I have to essentially figure out 2 to the what equals 64. And that x is how many number of bits I need to say where I am within a page for this example. So to not get your calculator out because you solve this log 2 as blah blah blah, that is slow as hell. So I will show you. You should only have to memorize 2 powers of 2, and then you could probably memorize less. I'm a bit slow. I can only multiply by 2 2 or 3 times, but if you remember 2 numbers, that's all you need. So if you remember that 2 to the 5 is 32. Just remember that, and then that 2 to the 10 is 1024. If you know those 2 numbers, you can figure out the rest by just multiplying by 2 a few times. Every time you multiply by 2, the exponent just goes up by 1. So if I know 2 to the 5 is 32, then 2 to the 6 has to be 64. Whoops. I don't have to do any complicated math. The only level of math I can do is multiply by 2 a few times and add. That's about all I can do, but for this course, that's all the math you need to do. Things need to be real fast. So that's also why you can bring your calculator to exam, but if you're using your calculator, you're going to be 5 minutes slower than everyone else that's doing something like this. So in this case, for my virtual address, well, we figured out how many bits we need for our offset. That was 6 bits. So how many bits do I have for my virtual page number? 2, I hope, right? Like I said, I can only do a bit of math at a time. Subtraction is one thing I can do. So 8 minus 6, that means 2. Why is it 8? Because it comes from the size of the virtual address. So if that's the case, how many virtual pages do we have? 4, right? Because the number we have corresponds to how many number of virtual pages we can actually index. So we have 2 bits, so we could actually index 2 to the power of 2 pages. So 2 to the power of 2, it's only multiplying by 2 once, or yeah, 2 times 2. I can do that, so that's 4. Any questions about that? All right, then what's the next one? How many physical pages can I support in this system? Anyone? Yeah?
2 to 4.
What? Yeah, and what's 2 to the 4? 16, right? So same thing for the physical address. It looks like this, and the offset is going to be the same, which is 6 bits. So what's left over for the physical page number? Well, 10 minus 6. I can do that too. That is 4 bits. So the number of physical pages we can address is 2 to the 4, which is just 2 to the 5 divided by 2. So that's 16. All right, next question then. How many entries would there be in the page table? Four, right? So this is a trick question, kind of. There's just one entry in the page table for every single virtual page number. It's just an index. It's just how you look up, how you know what to access in the array. So it will always be the same as the number of virtual pages in this kind of a system. And also, there was a hint there. It gave you a page table. It had 4 things in it, so you could probably figure it out from that. So this page table is a short form of a page table where for this, it's a page table full of physical page numbers, and it's written like an array. So each of these is a physical page number. And then the index of each one of them, so it'd be like 0, 1, 2, 3. Well, that's the virtual page number. That is how we look it up in the array and know which element we actually need to use for a translation. So then the question said, well, oops, if you have virtual address F1, what does that translate to? What physical address does that translate to using this page table? So this is where it gets a bit more of a pain because our offset that we don't have to translate is 6 bits, not a multiple of a hex digit. So I can't just kind of chop it off. This gets annoying. So this is why you were drilled on like binary and hex and all that stuff. It's to prepare you for this, I guess. So the easiest thing to do, believe it or not, is to just write this number out in binary. So let's see if we remember stuff. So what is F in binary? Yeah. Yeah, F is 1, 1, 1, 1. What about 1? So it's hex, so there has to be 4 bits. So if it's 1, hopefully it's just 0, 0, 0, 1. Right? So another little trick for remembering how to translate from hex to binary. You only really have to remember one really important one, and then from that you can figure it out. So just remember that A is 1, 0, 1, 0. What's a good way to remember that? Well, A is supposed to represent a decimal 10. So just write 10 out twice. A is 10 two times, and then past that, you just have to add a bit. So like B would just be adding a bit in the least significant spot, so B would be 1, 0, 1, 1. Just write this down. You can work out the rest from knowing this one. So if this is our virtual address in binary, and we don't have to translate the offset part, which numbers are part of the offset that I don't have to translate? So like, don't have to translate these 6? No, other way, right? So the offset is at the least significant bits. So this represents my offset. So when I translate that to a physical address, so means I don't have to touch them. So it would be 1, 1, 0, 0, 0, 1. So that is the offset part of my physical address. So that would mean that this is my virtual page number. So what is 1, 1 in normal decimal? 3, right? 1, 1 is just 3. So I would go to my page table, look up what I need to translate this virtual page number to. So it is 8, right? So instead of the virtual page number, I just write the physical page number as indicated by this page table. So what is 8 in binary? Yeah. 1, 0, 0, 0, right? 3 zeros. So we just write out 8. 1, 0, 0. And now if we want to translate this back to hex, we just start grouping in groups of 4 from the back. So that's one group, that's another group. So the physical address we end up with would be, what is this in hex? 1. What is this in hex? 3. What is this in hex? 2. So given this page table, if a process tried to access virtual address F1, it means it would be translated to physical address 231. Everyone see how we got that? Bueller, we're good? All right, so this, okay, usually people are already lost by now, so this is good. We're much better than previous years. So, some other fun things. So each process, like I said before, gets its own page table. So what happens when you fork? It will copy the page table from the parent. So part of being an exact clone of each other, that means it will copy the page table and all their virtual memory will be the same. So what the kernel actually does as a trick to make fork really, really fast, it copies the page table, and both processes have the same translation if the same virtual address points to the exact same physical memory. And if you only read information in both processes, you can actually share it, and it's really, really fast. So you don't have to allocate double the amount of memory. They both just share it. And then one of the things the kernel does is turn off the write bit to that memory, so it can tell if one of the processes tries to modify memory. Then if one does, the kernel will then create a copy of that page and then separate them out. So it changes the mapping in both processes. And that optimization is called copy on write. And you get to do that for lab 3. So that will be fun. So there's also a big problem here. So we might have noticed that, hey, this page table has 2 to the 23 entries. If you put that in your calculator, that's a lot of entries. So there are 2 to the 23 entries, and each entry is this big, which is 64 bits or 8 bytes. So 8 bytes is like 2 to the 3 bytes. So that means this page table is 2 to the 27 times 2 to the 3. So that's 2 to the 30 bytes. This page table is 2 to the 30 bytes, which is 1 gigabyte, and like real gigabyte, which sounds really bad, right? Yeah, that poses a problem. So you can also see why this index, the virtual address, is small, because it essentially corresponds to the size of this page table. So if we just made a 40-bit virtual address and just bumped this up to 28 bits, well, suddenly your page table just gets twice as big. So now it would be 2 gigs if we did something like this. So you can see why we would restrict the size or the amount of number of bits we use for the virtual address, because it corresponds to the size of the page table, while just this physical page number corresponds to the size of the entry, which is just always going to be 8 bytes in general. So we have that issue. Yeah, so we have that big issue that we will tackle later. You also might be thinking, this seems like a lot of work. So like in the sub-process lecture, and also in your create, you do like or in your lab 2, minus a few things. You basically always do a fork followed by an exec. So assume we're still in a world with a gig page table. Well, we wouldn't need to copy a huge page table if we exec directly afterwards. We are executing a new program, and it would reset the page table. That process would, it would reset the page table for that process for the mappings for that program. So it's a bit of a waste to copy the page table in that case, and there is a special system call that will actually not copy the page tables. So there's a system called vfork, and that makes the page tables the same in both processes, which also means that if you modify memory in one process, the other process can immediately see it. So they only have the system call with the intent that you immediately call exec, and then if you try and modify anything in either process while they're both active, that's undefined behavior, and the kernel's allowed to do whatever it wants. So this is only for like very performance sensitive applications, so you get some control over what fork does. So what we saw today, we use pages for memory translation, divide memory into fixed size blocks, typically of that 4096 page. Oh, wait, also before, a little aside. So you might have noticed I wrote GIB and not gigabyte. So that is very intentional. So in computing, generally we like powers of 2. So 2 to the power of 10 is generally like a kilobyte, and I'm going to write an I here. 2 to the power of 20 is like a megabyte, and 2 to the power of 30 is a gigabyte. Looks like a bit weird, I'm writing that little case I, because a gigabyte is actually not well defined. Neither is a kilobyte, neither is a megabyte. So for some people, they believe in powers of 10. So some people will call a kilobyte 10 to the power of 3, which is 1,000. And that is also a valid definition of kilobyte. So whenever you see kilobyte, it could mean 10 to the power of 3, or it could mean 2 to the power of 10. And you might notice that 2 to the power of 10 is slightly bigger. That's at 1024. So it would go up like this. So this is also why, if you have bought like a 500 gig hard drive and tried to use it, and it says it is only 400 and something gigs, because this number is what they sell you, that is the marketing number. If you look at the fine print on the hard drives you buy, they'll say 1 gigabyte equals 1 billion bytes, while your computer thinks a gigabyte is this. So it reports that. That number is way bigger than what they sell you, so it's going to report a much lower size than what you actually bought. So that's the differentiation. This little I in that, it always means powers of 2, and if you just see gigabyte, you have no idea whether it's powers of 10 or powers of 2. So that is your fun aside for the day. Yeah.
So I'm so confused. Like when you said that, like if you fork a process, you create the same table for itself until like you write to it
Yeah.
in memory. So like okay, let's say like you need to like change that table. Like you just like randomly like choose like this mapping algorithm or something. Like how do you know that map algorithm doesn't like point to another map?
So the kernel is the only thing that keeps track of the page table. So the kernel is the only thing that's managing it, so it would know. So like, for example, you could have, you know, process A, process B, and say this is their same virtual page for whatever reason. Well, the kernel could map both of those to the same physical memory. Right? And if they both read it, say like it just says x equals 1 or something like that. They could both read it. If at the time of the fork x was 1, they're both happy, right? So the only thing that happens is whenever one of the processes modifies x, let's say process B modifies x, then the kernel is going to grab a new physical page and do the update to x there, and then change this mapping in process B. So now process B will point to this physical page, which is different than the one for process A. So, and this, don't worry about this, we'll get into this in the next lectures too. But this is generally how it works. So, whoops. So today we use pages for memory translation. Divide memory into fixed size blocks. Only have to translate once per block. Don't have to translate the offset. Pretty fast. Because page tables are basically just an array. The array is indexed by the virtual page number and its array of page table entries. The only thing we care about really that's in a page table entry is the physical page number and 3 flags: valid, read, write. And we have a new problem on our hands we get to solve in the next lecture, that this page table is huge and our program's probably not going to use 512 gigabytes, so we should probably do something about it. So that is where I will leave you off for the next lecture. So just remember, pulling for you.